Hello everyone. In this video I'm going to quickly go over electric charges and forces. And main idea here is one, understanding the charge model and how to use it to explain electric phenomena and develop an understanding of it at the atomic level. So charges and forces, we all know from our life that when we rub things together, they get charged, electrified, and we can get shocks like zapping, like happens here with our finger and doorknob, or touching a Van de Graaff generator and our hair goes crazy like in here. Or we can rub a balloon on our cat's fur, and then the fur and the balloon will attract each other, and we can make our cat look crazy. So how does that happen? We can make small experiments to test all these. In this experiment one here, we have unrubbed, uncharged plastic rods. One can move freely, and one we hold in our hand and put them close to each other. Nothing will happen. However, if we rub both of the rods to a wall, they will be charged. This guy will be charged and this guy will be charged. And since we rub them in the same way to the same thing, they will get the same charges and same type of charges, right? And they will push on each other. They will apply a force on each other if we put them close by. These forces are called electric forces, also Coulomb forces. We'll talk about that more in the next lecture. And they are either pushing and pulling. If we have same charge, they will be pushing. Another example could be rubbing a glass rod to a silk. They will also be charged. And if we rub two glass rods to silk and do the same with the as we did with the plastic rod, we will see them pushing on each other. We'll have forces in opposite direction. And it's very important to notice here that these forces will be action-reaction forces. So they are equal in magnitude and opposite in direction. If we, however, have a rubbed glass rod, put it close to a hanging plastic rod, they will attract each other, or vice versa. A rubbed plastic rod, put it close to a hanging glass rod, they will attract each other. Still there are forces in between, still the forces are in opposite direction and equal in magnitude. So still they are action-reaction forces. I have little space here. I'm showing forces small, but they are vectors. They're not to scale. Keep in mind that they're always action-reaction forces. Similar things here. If we have two rods charged, this rod, let's say, has one type of charge, is actually going to be negatively charged. We give charges names as positive and negative historically. So assume both of these are charged. We put them close to each other, they will be pushing on each other. So there will be forces in opposite direction and equal in magnitude. And that's how we show vectors, right? If we increase the distance, let me show the distance in between here, approximately this much distance. If we increase that distance, let me call that D for distance. If D increases, let's sign for increasing, force decreases. This is a very important information about force being inversely proportional to the distance in between. Also, if we rub these more and increase the charge, we're going to use symbol Q for charge. If we increase any charge. Meaning it could be increasing on this rod or on that rod, doesn't matter. If the charge increases, if Q increases, force also increases. So this force is again what we call electric force or Coulomb force. It's very similar to gravitational force. It's directly proportional to the charge, and that could be compared to the mass for gravitational force, and inversely proportional to distance. In summary, we have like charges. They repel each other. They apply forces equal in magnitude, opposite in direction, and they push on each other, repel each other. Either it could be plus charges or minus charges, and if we have opposite charges, they attract each other. Although we said F increases with increasing Q, that's also a note, and F decreases with increasing D. D is distance here and Q is charge. I'm going to quickly pass these charge diagrams. Usually we have an idea about them, but we, again, as I mentioned, we represent charges. We call them plus and minus. This is just a historical choice. We could call them anything, but what we know is there are two types of charges, and like charges repel and opposite charges attract. What happens in more detail is if we, for example, rub the charge rod to wool. What happens is one takes or gives negative charges, the others also does the same. For plastic and wool, before we rub them, each are neutral. So if something is neutral, it means it still have charges, but it has two types of charges, all cancel each other. So if I have a minus, I have another one plus canceling it, the same here, and so on throughout. And the same goes for the rod. If we rub them together, some negative charges from the wool goes to the rod. So imagine charges are flowing here, and after a while we have overall excess of negative charges on the rod, and excess of positive charges are left on the wool because it lost some negative charges. Only negative charges moves. So to be exactly correct, we should always talk about negative charges moving. However, for simplicity, if you assume positive charges are moving, the result will still be correct. It still works, because if two negative charges move from wool to the rod, I have extra plus charges here, extra minus charges there. I could easily say, okay, plus charges move from rod to wool, and I'll get the same result. So if you hear some other people talking about positive charges moving, physically it's not correct, but the results will be the same. So after a while, as one object loses charges, the other gains them. One will be overall positively charged, wool is in this case, and one will be overall negatively charged. I'm going to show these charges moving as well here. I'm going to stick with negative charges moving, but keep in mind, if the positive charges move and you assume that the results are correct, physically it's not correct though, and I'll get to that in a bit. So wool lost some negative charges to the rod. Rod became negatively charged and wool became positively charged. Here's how we show them symbolically. We only show excess of charges. Wool actually still have negative charges, but it has a positive excess, so we show that. And rod has excess of negative charges, we show that. And all is similar with the silk and glass and so on and so forth. And this page is a summary of charge model part 1. Same charges repel, opposite charges attract, and the force they apply to each other are action, reaction forces. So remember, action equals reaction, so they are equal to each other in magnitude, but opposite in direction. Also, force is directly proportional to the charges. and inversely proportional to the distance. Distance is shown here as r. We can make many different experiments to understand this idea of charges and charging better. There are many examples here. I'm going to quickly go over several of them. One, for example, if I charge an object, so assume I charge this rod, touch it to a metal object will take some of the charges. Assume this guy has positive, and some positive charges will move here. Okay, I said positive charges will move here. Actually, what happens if this guy has positive? Some negative charges from metal will go to the plastic, and we will have overall positively charged two objects. Let me go back and tell you exact physics here. Assume this, this is a plastic actually, it will have negative charges. Assume this is a plastic and it has negative charges. 3 negative charges, or let's say it has 4. And I touch it to metal. What will happen is, in this case, is that some of the negative charges will go to the metal. And metal will have some, let's say 3 of them went there, 2 of them stay here. Plastic will still stay negative, but metal will have some negative charges, so both are going to be now negatively charged. Going back, let me assume this is glass, I rubbed it and it has positive charges. Let's say it has 5 positive charges. What will happen when I put it close to the metal? Metal actually is initially neutral, it has plus minus all together. Physically, what will happen is some minus charges will go to the plastic because it has a lot of positive charges. Those minuses will come, neutralize some positives. Let's say 3 of them came to the plastic, neutralized 3 of the positive charges. Since 3 electrons went to the plastic, now, let's go back. Now on the metal ball, what I have is one. Okay, let me delete and rewrite. 3 negative charges are left, so I'll have 3 positive charges now alone. Overall, metal is positively charged. Rod is also positively charged, but less positive because some of its charges are neutralized by these incoming electrons. That's perfect physical way of explaining it. But if I just want to, for practical purposes, if I just, let me go back, and if I just say this, that would also give me the correct answer. If I have a positively charged plastic, neutral metal, assume it has no charge, don't show these internal charges, and say some of these positive charges goes to the metal. Let's say 3 of them went to the metal and 2 of them are left. Now everybody is positively charged. 2 charges here, 3 charges moved there. So saying the positive charges moves also gives me the correct answer. So feel free to say so, but keep in mind physically only negative charges move. All right. I can also have a charged object, put it close, touch the metal, charges will be shared. Let's say this is negative, some negatives will go here. And I have another metal ball here. I have plastic rod in between. Plastic is an insulator, so it will not let the charges go from the metal on the right to the metal on the left. So this metal will not be charged. It will stay as no charge. If I have a metal rod in between, this is a conductor, and it will let the charges go. So if this guy had negative, some negative charges will come here, they will move through the metal and will come to the other metal ball. The idea here is if I have a negative on this, the negatives wants to push on each other, so they push on each other, they keep pushing until they go as far as they can, which is why they go through this metal rod to the other metal ball. But insulator doesn't let that happen. So this metal ball, in this case, in the middle case, cannot get any charge. I'm going to skip some parts over here, but we have conductors and insulators, as I talked in the previous page. Conductors easily let those negative particles move, negative charges move inside them, and insulators do not let that happen. That's the difference in between them. Some other examples here, similar transferring charge. If I have an object and it's charged, I touch it to another object, charges pass to that object, I'm charging the second object as well, like the metal ball and the plastic bar here, rod here. That's called charging by conduction. There's another happening in the charges is charges are not really moving, are only separating inside the object but not moving the object to somewhere else. Like in this case here, if I don't touch this positively charged rod but put it close, so this is charged, I put it close to this metal ball, it's actually neutral. What will happen if it's not touching is that we have positive charges here, it will pull all the negative charges or many negative charges close to itself, so there will be a charge separation inside the metal ball. This is what we call polarization. Second thing that is really interesting and nice here is that since those negative charges came close to the positive charges, they will be pulling. These positive charges here still push on each other with the positive charges in the rod, but as it's shown in this figure here, negative charges are closer to positive charges, so the force on negative charges is larger by the rod, positive charges on the rod, than the force on positive charges. So overall, first this rod coming close to the metal bar, first will do the charge separation, cause the polarization, and then attract the metal ball. So first polarization, then attraction, which is why we say if we have a charged object and a neutral object, this is charged here, this is neutral, they will attract each other. Come close, attract. Another way of charging is induction, and induction involves polarization as well. Actually, induction is charging by not touching. Conduction is charging by touching. So I'm gonna put here is touching and not touching. Inducing, right? How can we do this? Here is one here, conduction, right? We charge something, touch it to another one that is not charged, and charges move to the other one. Now everybody is charged. They share the charge. And here's an example of induction here. If I charge these two, look at the middle diagram here, two metal balls A and B are not charged first, neutral. They have plus minus charges are canceling each other inside. Neutral means the same number of plus and minus charges. That means empty. If I put a charged object close to them, here I have a charged balloon, negative charges. What does negative does is pushes all the or most of the negative charges as far away as possible. So those negative charges moves from A to B, many of them at least. Now overall, as my balloon is still staying here, A has overall positive charges, excess of positive charges, B have excess of negative charges, while I'm still keeping my balloon in here. I separate my insulators, I separate my metal bars, sorry, by holding on the insulator part here, not the metal ball. Otherwise the charges will move through my body and I'll change the situation. So first separate the balls and then move away the balloon. What will happen is whatever the negative charges went to B will stay there. So B will be overall negatively charged and A will have excess of positive charges because a lot of negatives already moved to B. That's called charging by induction. Without touching the balloon, I caused A and B be charged. There are different ways of doing this, but that's the general idea here. Another way could be I put balloon close to another alone metal ball. Then I touch the ball on the side where the negative charges are accumulated. Those charges will go to the ground through my body, and then I remove my hand, remove the balloon. First I remove my hand, then remove the balloon, then remove the balloon. Now my metal ball will be overall positively charged. That's by induction. On atomic level, what happens is that we have positive charges as protons in the center of the atom. Negative charges are around the protons, farther away, which is why positive charges don't move a lot. Negative charges are outside, outskirts of the atoms, they can move easily. But cannot, the positive charges or protons cannot. If I totally ionize something by heating it too much and separating positive and negative charges, then that could happen. So we could have a positive ion by heating atoms and freeing some electrons from them. Sometimes we can also give electrons, so ionizing atoms is possible. That situation changes. But overall in nature, mostly we have neutral atoms. Ionization is possible. We won't be really going into details of these, but what we want to know is why the electrons or negative charges move easily is because they are outside and around the protons. Protons are more like in the center, which are positive charges, and they can't move easily. Since electrons and protons are maintaining charges, when I have a material, there are many atoms in there and many electrons and protons, and those electrons that are outside of the atom can move. So let me just represent proton as a plus, electron as a minus around the atom. It's actually a kind of cloud if we want to be more. Okay, I didn't do a good job here. Let's just put one negative, one electron. Their charges are the charges, and we have symbol unit as Coulomb, the name of the scientist who worked on the electric force and charges, which is why the electric force is also called Coulomb force. And each electron and proton have the same amount of charge, electron being positive and proton being negative as the elementary charge. This is here an elementary charge, and it's equal to 1.6 times 10 to 19 coulomb. Proton has positive version of it, electron has negative version of it. If these are some examples I'm gonna very quickly go over, but if I have something charged, again we can charge other things with it by touching, right? By touching is conduction. charging by conduction, by not touching, by inducing, let's say, of course it's induction. So here we see a charged rod going close to two neutral balls. That's induction, right? And it's a question about induction. What it says, I have two metal spheres, 1, 2, initially neutral, and I do the steps. The charged rod is brought near, not touching. The charged rod is then removed. The spheres are separated. And go thoroughly with this slowly, thinking about what happens to charges. You can easily solve these problems. Plus charge, coming close, not touching, it will cause a polarization in the charges. And what it will do is it will pull negative charges to itself, as many as it can, right, as close as possible. Push away the positive charges. Positive charges will not be moving a lot, but negative charges from this second ball to the first will be moving, right? It can push the positive charges a little bit in atomic scale, stretch the atoms maybe a bit, but it can't really move them a lot. It will be electrons or negative charges moving. So this will happen while my charged rod is here. That's A. The charged rod is brought near. Then what happens in B? The charged rod is then removed. Then I take this dude away. Balls are still touching. Removed, right? A brought near. That happened, but I removed the charged rod. What will happen? Let me show B in blue. These electrons will go back. They have a way to going back. They will right away go back to plus charges here and go back to their original place. Everybody will be neutral then. These go back, and this guy is neutral, and that guy is neutral. And then even if I separate the spheres, they won't be charged because they became neutral before I separate them. So the answer will be 0, 0. This one is similar. This case, steps a little different. The charged rod is brought near, spheres separated, then charged rod is removed. So I bring this dude near. That's A. Charges are polarized, negative charges came here. Let's say positive charges went there or left alone here to be more physically correct. Again, if you say it the wrong way and assume positive charges moves, the result will be still correct. Let's say now while the rod is here, I am separating my spheres. Separate, that's B. So if this plus is still here, it's still pulling negative charges towards itself, and I separate my spheres, the negative charges will stay here, positive charges will stay there. Overall, this guy will be negatively charged. So it will have a negative charge axis. And this guy will be positively charged. Axis. Now, although I remove my rod, nothing will change. Let's see. Move the rod away because these are separated and the charger will stay. Now one will have negative charge and two will have positive charge. if we touch charged objects to each other, they share the charge always. One could be neutral, both could be charged objects touching, they share the charge. The bigger object takes more charge. I'll write this much. They share the charge according to their sizes. Let me put that here. If I have equal sizes in here, equal size, they will share it equally. If I have a larger sphere, for example, if this guy was larger, it would take more charge, and directly proportional to their sizes. So this question is related to that. Identical metal spheres are initially charged as shown. P has +4 nanocoulomb, that's nano. Q has -2 nanocoulomb, and R has -1 nanocoulomb. Let's see what's happening here. Spheres P and Q are touched. First we touch this. Let me put step 1 here. This guy is not touching yet, so it's not in here. What will happen in step 1? All the charges will add. Let me call this Q1. It will be +4 nanocoulomb plus -2 nanocoulomb equals +2 nanocoulomb, right? And they have the same size, so they will share equally, touch, have the total, and then share equally because they have the equal size. So each will have +1 nanocoulomb each. After the first step, here's what P has, +1 nanocoulomb, what Q has, +1 nanocoulomb. What happens next? Then spheres Q and R touched. Now we leave P, we are touching Q and R. This is step 2. Since I'm not touching P anymore, after step 1 it has 1 nanocoulomb. If I'm asked to find the charge of P, it would be 1 nanocoulomb. But if I touch Q and R, what happens? This guy has 1 nanocoulomb plus -1 nanocoulomb. Let me do this part here with the red. Step 2. Q2, let's call, will be +1 nanocoulomb plus -1 nanocoulomb. It's 0. So we're going to have 0 charge after step 2, right? 0 and 0. What is the question asking? After the charge on the sphere R will be 0 nanocoulomb or coulomb. All the questions are solved similarly here. I have the solution here, but I wanted to go over it. See you in the next lecture.